All right, pre-calc 5.6 logarithmic and exponential equations. Just building on what we learned last time, we're now going to use that to solve some equations. Okay, so let's get right to it. Example 1, solving a logarithmic equation. Okay, so using the properties that we learned last time now, you guys should be able to see some patterns here. If I were to write this as an exponential function, what that would look like is it would look like this. It would look like x to the fourth, right? Because I brought the 4 out here. So I know that since this 4 was brought out, like if you think about what we did in reverse from last time, that this originally was log base 6 of x to the fourth, right? And they pulled that 4 out front. So I have x to the fourth. Technically the log base 6 is still here, but since it's on both sides, I don't have to worry about it. I can drop the logarithm out. So I get x to the fourth is equal to 16. Okay, and again, it's only because the log base 6 is on both sides that I can do that. Now I can solve this pretty easily. I know that 2 to the fourth power is equal to 16, so x must equal 2. Technically, it also equals negative 2, right? Because negative 2 to the fourth is also 16. But what you have to consider here is that this guy can never be negative, right? Because it is an exponential. So we do not include the negative. It will just be x equals 2. All right, so that's example 1. And they show you also how to graph this on your TI. To graph it on your TI, you're just going to graph each side of the equal sign separately. So notice, one of the graphs is this guy, one is this guy. It's each side of the graph. And they convert it to log base 10 using the change of base formula. Okay, so use your change of base formula and you can graph these. When you do, the intersection is exactly where the solution is. So this thing intersects at x equals 2, and they give you what the y value is there. Okay, you could just use your solver to see where the intersection is. And that is another way to get a solution to one of these. Okay, so just like everything else that we do, we can graph and get a picture of these if we choose to. All right, I don't know how much of that they're going to make you do in the homework. So example 2, solving a logarithmic equation now with exponentials. Sorry, not exponentials, quadratics. So here we have a log base 5, log base 5. We can't cancel it because there's not a log base 5 on the other side of the equal sign. All right, so let's rewrite this at least and get it all in one logarithm. So to do that, I can say that this is the same thing as log base 5. Since these two things are being added, I know that originally they were multiplied together. So this would be x plus 6. Sorry, I don't have my stylus, so my handwriting's not as neat as usual. X plus 2. Okay, and that's all equal to 1. Equal to 1. Okay, so if you think about this now, this is saying 5, if you think about it in exponential form, 5 to the first power is equal to those two things, right? X plus 6 times x plus 2. All right, so if I rewrite it as an exponential, we could say 5 to the first power is equal to x plus 6, x plus 2. Okay, well 5 to the first power is just 5, right? So what I can do now is I'm going to say 5 is equal to, and I'm going to go ahead and FOIL this out. I get x squared plus 8x plus 12. Okay, if you wanted to solve this, you need that quadratic to be equal to 0. So you can subtract 5 from both sides and be left with, and now I guess I need to move. Well, here, I guess we could pick up here. What you'll be left with is, if you move this, this is where we left off, you'll be left with, you can subtract 5 from both sides, you'll be left with this guy, right? And that guy plays nicely, factors nicely. You get x plus 7, x plus 1. So, tempting to put both of these solutions in, right? Must be negative 7 and negative 1. But remember, each one of these, since they are both logarithms from the beginning, have to be greater than 0, right? I can't have a negative in there. So if I plug a negative 7 So what you could do, what I like to do, is I like to just check them, right? I like to check my answers and go plug those each back into my original logarithm and make sure it works. So if I do that, if I plug a -7 in here, -7 plus 6 gives me a -1. So therefore, I know -7 can't work. Okay, -1 does work, however, because -1 plus 6 is 5, -1 plus 2 is 1, so this one does work. Okay, so when you're done, what I encourage you to do is plug these back into the logarithm pieces of your original equation to make sure that those don't go negative. All right, so just be careful with that, because it's tempting just to put both answers, because that's what we've always done, but now we got to plug it back in and check it and see if it's valid. Okay, let's keep cruising. So they show you how to graph this, right? And again, I'm not going to make a big deal about graphing these, because I think the algebra piece is probably a little bit easier. It's a little tedious to graph these, but anyway, they do show you how to do that. Here in example 3, we have a natural log problem. Again, same kind of deal as a basic logarithm. This is just saying log base e, right? So that's all the natural log means. So here, we're adding here within a logarithm, so I know that that's multiplication, right? So, and notice that the natural log is in all 3 pieces. So I'm actually, right now, I can drop it out. Okay, so I have x times x minus 1 is equal to x plus 15. Okay, if you FOIL that or distribute that out and move things to all to one side, you're left with this. You get x squared minus x equals x plus 15, which is x squared minus 2x minus 15 is equal to 0. Okay, if you go to factor that thing, your two factors are x minus 5, x plus 3. Okay, negative 5 times 3 gives you positive, or negative 15, and negative 5 plus 3 gives you negative 2. Now my two solutions to this would be 5 and negative 3. I must test those. Okay, well, if I plug a negative 3 into my first one there, my first logarithm in the original equation, it would be negative, right? So negative 3 does not work, so therefore 5 must be my answer. All right, so they show you that here on the next few slides. They show you how to graph this thing again. And then we're off to objective 2, solving exponential equations. So this is kind of very similar to what we just did, but now we're going to be using our change of base formula quite a bit. So on example 4, we have 3 to the x is equal to 7. Well, if we think about what this is in terms of a logarithm, this is the same thing as log base 3 of 7 is equal to x. Right, well, you know how to solve log base 3 of 7. You could put it into your TI, or you can just use your change of base formula, right? Which is just saying that the log of 7 over the log of 3 is equal to x. Here, they show you that they're using the natural log of those things. That's okay. That's just saying log base e of 7 over log base e of 3. It'll give you the same answer. All right, so it doesn't matter if you use log base 10, log base e. Really doesn't matter which log you use. As long as it's the same, it's going to cancel out, right? It's going to be perfectly within the, I guess you would say, I don't know. It would be legal. Let's say that it would be legal as long as the logarithms are the same in your change of base formula. It doesn't matter which one you use. A lot of times people do use the natural log, so I think that's why they show it here, but it doesn't matter which one you use. So I just wanted to make that clear. Let me cruise on. Make sure that if in the homework they say approximate solution rounded to some near decimal place, that you actually put it in your calculator. If they say exact solution, just leave it in this form. Just leave it in the form natural log or log base 10 of 7 over 3. Okay. And then again, I guess they are going to show you how to graph these. Graph each side of the equal sign independently, see where they cross. Not going to take too much time with that here. So, for example 5, now we're going to solve this guy with a two-step. So we got to first divide by 7, right? So I get, you want to get the exponential by itself. That's really the goal. So you have 2 to the x equal to 4 over 7. If you wanted to write that as a logarithm, it would be log base 2 of 4 over 7 equals x. Okay, so how do I solve this one? Well, it's the same. I could take the log of 4 over 7 divided by the log of 2 and get my answer. Here again, they show it to you with the natural log. Okay, either way is going to give you the same result. It's going to be negative 0.807. And I encourage you to put it into your calculator, make sure that you're getting the same solution. Okay, so make sure that you're comfortable with this. Example 5, part 2, they show you how to graph that, right? So you can graph each independent piece. Where they intersect again is the solution. Example 6 is pretty involved, so pay attention to this one. If you think about what this is in terms of a logarithm, you have 7 to a power, right? So within that, I want to multiply that by, if I take the natural log of both sides, or you can take log base 10 of both sides, it doesn't really matter. I'll use the natural log because that's what they've been doing. But if I do that, what I end up with is I'm going to pull this exponent out to the front, right? So this is going to be x minus 3 times the natural log of 7 is equal to 2x plus 1 natural log of 2. All right. And that is, I put those in parentheses because it's applying, the natural log is applying to both pieces there. Okay, so the next step with these, you guys, is to essentially, you can't, so one temptation here is to, oh, let's divide both sides by 2x plus 1 and try to get these natural logs all to one side of my equation. No, you can't do that because we actually have 2 different bases here. Okay, so it's not that simple. What I need to do is distribute this log out to all of its pieces. All right, so if I do that, I have, maybe I need to scroll down here. So if you do that, what you end up with, the reason is I don't think I can do without my stylus. I don't know that I could write small enough to get all this on here. So we pulled it out front, right? So we were left with this. This is where we left off. Okay, so from here, if I distribute it out, take the natural log times x, natural log of 7 times x, and the natural log of 7 times negative 3. Okay, this is just the distributed portion of this, I guess is what you would say. So I could do that, and I can also do it on this one. So I have the natural log of 2 times 2x. Okay, and they, in this same step, they pulled the x out of that. They pulled the x to the outside. And then the natural log of 2 times 1. The reason they pulled the x out here is because eventually we're going to pull it out of everything. Okay, so they just kind of skipped a step there, which I don't love. But that's all right. So now what we need to do is we need to get all of our x terms to one side and all of our non-x terms to the other side. So what they did was they took this guy and they moved it to the other side, and then they took this guy, which has no x, and moved it to this side. Okay, so get all of your x terms to one side of your equation. So we want to isolate that variable and get rid of it, right? We want it to, well, not get rid of it, but solve for it. Okay, so once we've done this, okay, it becomes a factoring game where we're like, okay, is there something in both pieces here? Well, yeah, that's what we've been working on. We're working on getting x in both pieces, right? So we can take that x out. If you take the x out, you're just left with the natural log of 7 minus 2 times the natural log of 2. And then on the other side, we still just have, our non-x terms, 3 times the natural log of 7 plus natural log of 2. Final step here is to get x by itself by dividing both sides by the natural log of 7 minus 2 times the natural log of 2. And now we don't have any x's on our right side of our equation. We can actually just put that straight into our calculators, and when you do, you will be left with 11.670 hopefully. So make sure that you're comfortable plugging those in on your calculators, and don't forget that if you're going to do this all in one piece, that this has to be in parentheses, right? You're going to divide that full answer by this full answer. So just be careful when you're plugging that into your calculator. Calculator needs to know what is truly fully being divided. So just don't forget your parentheses. Hopefully they just let you leave it like this in your homework. Oftentimes we just leave it like this, so the exact solution would be that guy. But if they have you round it, just do it out on your calculator. All right, guys, I think I'm going to stop the video right here. We'll talk about this one in class, example 7, and yeah, we'll catch you